Right now, the Indian Air Force is facing a serious delivery bottleneck. They are waiting on U.S.-supplied General Electric F404 engines for their light combat aircraft, and the delays are stacking up. In response, a popular alternative has surfaced. Just swap the American engine for a French one. The jet caught in the middle of this debate is the Tejas Mk1A. It is a highly capable, fly-by-wire fighter. When supply chains freeze, public and political discussions often frame engine swapping as a simple procurement fix. The logic sounds straightforward. If one supplier is late, you unplug their hardware and plug in a competitor's to keep the assembly line moving. In aerospace engineering, however, an engine is the core of the platform. Switching it out requires tearing up the airframe and redesigning the internal architecture, a grueling process that traditionally demands 5 to 7 years of re-engineering and testing. Aerospace companies claim that new artificial intelligence tools have digitized this entire process. We need to look at the math to see if AI can actually shrink that impossible timeline, or if an agile engine swap is a marketing myth. This table shows the exact physical and performance specifications, contrasting the baseline American GE F404 against the French Safran M88 family. If you look at the thrust column, the standard French M88-2 puts out only 75 kilonewtons of power compared to the F404's 85 kilonewtons. That deficit forces engineers to use an upgraded variant, like the M88-4E, just to match original payload capabilities. Even with the thrust matched, the physical dimensions present a severe problem. The French engine is 37 centimeters shorter and roughly 175 kilograms lighter than the American power plant it replaces. Modern fighters like the Tejas are built with relaxed static stability. They are intentionally designed to be aerodynamically unstable to increase agility. When we pull 175 kilograms out of the rear of that airframe, the center of gravity drastically shifts forward, throwing the jet completely out of balance. Moving to a smaller, lighter engine does not create extra room to work with. It breaks the fundamental physics of the jet and mandates severe structural intervention. To bridge that physical void, engineers have to design highly customized load-bearing adapter mounts. These mounts must cradle the smaller engine inside the original engine bay while absorbing massive vibration and G-forces. Historically, aerospace engineers used a digital technique called topology optimization. A human drafts a basic 3D model, and software algorithms carve away the unneeded material, block by block, to save weight. Because this method starts with a human drawing, it is confined by human design habits. The weight savings max out early because the algorithm can only subtract from what is already there. This diagram compares that traditional method on the left with generative design on the right. Instead of carving a block, generative design algorithms use strict input constraints to organically grow geometries from scratch. This isn't theoretical. Researchers recently applied generative design to replace the engine mount on a Cessna 172 light aircraft. This matrix tracks the mass and safety factors from that Cessna test. The algorithm evaluated multiple iterations automatically, producing structural mounts that hit specific load requirements while drastically cutting down the mass compared to the conventional human-drafted design. The trade-off here is manufacturing. Generative design produces complex, alien-looking organic shapes that are nearly impossible to machine using standard tools. You solve the weight penalty, but you are forced to rely on highly expensive 3D metal additive manufacturing to actually build the parts. The second major hurdle is heat and air. The outer casing and nozzle of the M88 produce a different thermal exhaust footprint than the F404, and its compressor demands a different volume of intake airflow. Redesigning the rear fuselage heat shields and the air intakes to handle these changes used to require building physical scale models and spending months running them through wind tunnels to ensure the jet's aerodynamics and stealth profile remained intact. Today, development teams bypass physical iterations by employing deep learning surrogate models and high-fidelity digital twins. These AI surrogates simulate multi-physics environments digitally. They process real-time thermodynamic and aerodynamic stress loads on a virtual replica, calculating exactly how heat washes over the tail section at supersonic speeds. The catch is the data requirement. To trust a simulation enough to put a pilot in the cockpit, the predictive models must be trained on massive sets of historical flight data, which requires intense raw computational power. Digital twins successfully eliminate years of waiting on physical wind tunnel availability, but they shift the project bottleneck directly onto your computing hardware and software validation teams. Once the physical mounts and thermal shielding are solved, you hit the third invisible hurdle, the FADEC, or Full Authority Digital Engine Control. The jet's mission computers speak an American digital protocol natively. The new engine operates on a specific French twin-lane architecture, designed for platforms like the Dassault Rafale. This flowchart illustrates the digital language barrier. A translation layer must be coded so these two systems can talk perfectly. If there is even a millisecond of latency communicating throttle inputs, the results in flight are catastrophic. To bridge this, engineers place the hardware in a loop with neural networks. The AI actively monitors sensor streams and auto-tunes the fly-by-wire flight control laws, adjusting the software to recognize the new thrust curves and the shifted center of gravity. Rewriting the jet's digital brain is mandatory. Without AI retuning those stability algorithms, the new aerodynamic profile would render the fighter completely uncontrollable in the air. So when you stack generative design, digital twins, and AI auto-tuning together, how much time does the digital approach actually save? This stacked bar chart maps it out. The top bar shows the sequential old paradigm, totaling 5 to 7 years. The bottom bar shows the modern digital approach. By utilizing AI workflows, the time to physical manufacturing is compressed to 3.5 years. Cutting the timeline in half is an incredible engineering feat. However, 3.5 years of active development proves that swapping a fighter engine is still nowhere close to an overnight fix. When we apply this 3.5-year reality to the Tejas Mk1A, the picture becomes clear. Halting an active manufacturing line for 3 years to digitally redesign the airframe creates a massive production vacuum. You would effectively cripple current fleet deliveries to solve a temporary supply delay. Where this timeline compression becomes a strategic advantage is during the prototype phases of future platforms, like the Tejas Mk2 or the twin-engine AMCA stealth fighter. By running generative design and digital twins before the physical manufacturing blueprints are frozen, engineers can seamlessly integrate an upgraded or co-developed engine natively from day one, avoiding sunk physical costs. AI tools do not make an engine swap easy enough to band-aid a current supply chain crisis. What they do provide is the engineering speed required to secure structural and strategic independence for the next generation of combat fleets.